very happy to be, I think I'm for the second time at this workshop. And I'm surprised how differently looks Bristol from if you are located in a different hotel. So it's a really amazing city. I love it. And I will miss it once you sail away with Brexit. and you know, so how can I get a pointer here? Oh. Okay. So there is this unpronounceable word at the very beginning of this title, which a little bit differs from the one which is in the program, and you will pronounce it. English is a monosyllabic language, so let's say for you it may be difficult to pronounce it. For me, it's always a disaster. So, but you know it, okay? So this is not a planned research. It's something on which I stumbled, and I'm kind of happy that I did. Okay. So the thing is that let's say the idea is that I will show you a new look at the polarization of quantum light. And then I shall show you, let's say, some ideas how to gain from analysis of how should we use, let's say, polarization parameters for quantum light in case of correlations. What thinking about it gives us in other situations. Okay? So, and I will skip this. Okay, so let me go to remind you some things about polarization. Okay, so polarization was kind of, let's say, discovered quite early in the research of optics, but we started to understand it, let's say, with Maxwell, because we started to understand anything about classical light and its relation to electromagnetism with Maxwell. So just look at something that does not exist, but it's a very nice example. When you think about basic properties, it's the electric field, and it's a plane wave solution. Okay, and so it has a lot of characteristics like the wave functions, the frequency, the phase, and that gives you the oscillation. Then you have an amplitude, and you know that the square of this amplitude gives you the energy of the wave, or rather intensity of the wave, because otherwise the energy is here ill-defined for something like that. And then you have this very tiny little vector, which is orthogonal to this one, and we call it polarization vector. And the thing is that the polarization vector, no matter how strong is your light, the polarization vector has the same length. It has a unit length if you consider such a way. Okay? And then let us move to 1852. And that was a very important year for optics, because Stokes, who is pronounced in Poland Stokes, because people are not aware that he's from the Isles. And so Stokes, in 1982, he introduced his parameters, which let's say they are about polarization of light, but really they are applied to chaotic light. Okay, so if you have a certain probability of certain waves appearing in your optical system and you somehow measure, then you can find with the Stokes parameters the so-called degree of polarization. Okay? So it is applied to much more complicated situations than this. And then, let's say, something like 110 years later, quantum optics emerged. Okay? Quantum optics emerged together with the invention of laser. And so people were building up the formalism for quantum optical observations. And the result of this work is like that. So let us take 1852 Stokes parameters, write them down the way they should look like in quantum formalism, and that will be our Stokes parameters. And these are quantum Stokes parameters. So let's say the moral of my talk will be that in situation when we talk about highly specific quantum phenomena, this is a mistake. Okay, so it's a wrong approach. Just to rewrite the old definition. And so you know that this object, if you can see it, is the photon number operator, and so let's say one of the Stokes parameters, the traditional one in quantum mechanics is the number, let's say if we assume, because Stokes parameters can be defined in terms of intensities, but if we assume a very trivial model that, let's say, the intensity measured in the given run of the experiment is the number of photons, okay? And so here's the number of photons in one of the exits of a polarizer, and that's the number of photons in the opposite exit, okay? And there's a minus between all them. And of course, we take as I three possible complementary settings of fully complementary settings of the polarizers, okay? And of course, there's one more parameter, which is the total power or whatever. In that case, the total number of photons, okay? So that's how we define it, and that's how we usually use it. Okay, and you can find a lot of books and reviews on polarization. We just follow more or less the same strategy, although some strategies are a little bit more refined, because we know that let's say there is let's say in fields where the photon number is undefined, and a lot of interesting things may happen. But still, it is more or less developments of the Stokes idea. And also, if you look at one of the encyclopedias of quantum optics, you will find the same things. And now comes, let's say, the idea that I want to present to you, and it's so simple that you will always remember if you listen to my talk. If you fall asleep, which is very difficult even in the most interesting talk not to avoid. In my case, I'm sleeping on every talk. But not the one that precedes my own talk. So Ephraim, don't worry. And let us imagine one run of your experiment. So imagine that you have a, let us imagine, let's say, operational situation. So you have a pulse source, okay? And let us assume that the pulses are not too frequent, okay? And then, let's say, when one pulse, let's say, excites the source, then you have some kind of emission, which is interesting, and you record all the photons that come from that emission. And then the next pulse is a repetition of your experiment. As you know, in quantum mechanics, even though people who follow different interpretations of quantum mechanics, the quantum states, no matter what they say, as underlying situation, it represents an ensemble of repetitions of a preparation, and therefore, let's say, then its results are averages, results that we get are averages, which are averages over very many preparations and recording of that. Okay? So let us now talk about single such events. So we have one pulse, and we registered, we set our polarizer at certain, let's say, angle or polarization, and it has two exits, and then we registered, and in this run, NIR photons in one exit, and NIR, and that's orthogonal photons in the other exit. So the new Stokes parameter will be the ratio, just ratio. And you look that the lovely thing is that it's natural. I think that Maxwell would have liked it because it's a normalized parameter. Okay, so in every realm, you just have such let's say one number which is between 0 and 1. Sorry, minus 1 and 1 because of this number. Of course, you should shout now that it's ill-defined because there is a denominator, but of course we do a trivial thing. Whenever nr is equal to 0, then that means that there were no photons, that there was no polarization at all, so we put this by hand as something that is equal to 0. So you see, in case of Stokes parameters, to put it short, you normalize your Stokes vector, if you like, after the averaging over the whole experiment, and also in quantum mechanics after averaging over the state. Whereas we average here, we first normalize and then we average. Okay, so, and this is kind of, I think you immediately know that if we first do something and then average, then we lose a little bit less information. And so now you should ask me whether it's possible to build a quantum operator. Yes, it's possible, and it's quite easy. Okay, so this is the average. I barely see it from this. So this is the average of my Stokes parameter. So here's the quantum state, and of course here are the number operators, difference in one exit and the opposite exit. That's the total photon number operator, and here are protective projectors. Okay, those projectors simply project out the vacuum. So then this ugly thing in the denominator is properly defined. Okay, because it never sees a vacuum state. Okay, and we also introduce a zeroth Stokes parameter, which is just the probability of having non-vacuum event. Okay, because as you see, this is this probability. Okay, and the lovely thing is that they behave like those objects. They behave like block vectors, and the funny thing is that they even for pure states, they behave like block vectors for mixed qubit states. Okay, so just look that the sum of the squares of the SI components of the new Stokes polarization vector is less or equal to the square of this object. So as you see, S0 is not a normalization, even in the case of a pure state. And of course, if the pure state is a fixed photon number state, so it's not a superposition of varying numbers of total number of photons, then we have the equality. Okay, and so the definition is useless. Okay, from the point of view of somebody who is designing a 3D cinema. Okay, because we never normalize in our eyes, let's say, in that eye and that eye, what is the polarization. Okay, and the more we have polarized photons, the more we see in this eye. Okay? So it's useless. But I will show you that it's not useless. But it's only for correlation. So let us take something that, let's say, we call, because we are in such a project, bright squeeze vacuum, and its application together with Maria Czechova. So let us consider 4-mode bright squeeze vacuum, which is just type 2 output of parametric ground conversion, which is used for creating polarization singlets when they are mainly only two photon of one photon here emissions, and with pump cranked up so that we have situations where we have uncertain number of photons in emissions. Okay, so as you see, it's a superposition of many photon emissions, and this is the theory of that. You can find it almost anywhere, and it's a superposition of such singlets. Okay, that's an two n photon singlet, and really this is a kind of super singlet of undefined total photon numbers. Okay, and what is very important, you can even generalize it, this object to using Hamiltonians, which have a lot of let's say, which can be kind of Schmidt decomposed into a lot of pairs of conjugate modes where the definitions are. But let us forget about it for a while. I don't know whether we reach that far. And so let us test whether it works in quantum, really quantum situations. And what is really the quantum situation? Basically, we know that if we have a, let's say, just a single pattern, an interferometric pattern, we are not able to tell whether it's quantum or not. The only, let's say, quantumness is in the act of discrete moments of registration. But otherwise, let's say, double slit picture of quantum light and classical light is just the same. Okay? So, but as we know, thanks to Bell and then to many others, the quantum mystery is hidden in the correlation. So let us try whether this new definition of polarization can be useful in detection of entanglement. Okay? And perhaps I will start a little bit in a different way. So these are the old Stokes parameters, those that were just copied from 1852 work and fed into quantum optics. And Baumeister and Simon in 2003, in a strangely titled paper, they have shown such a condition for separability for light which is emerging exactly this this device that I was telling you, strongly driven type 2 down conversion, where we have a lot of higher photon number components. Okay, so whenever this sum of the squares of the sum of the Stokes, sorry, there is a mistake. Oh my God, there should be a bracket. Okay, just like here. Okay. So whenever this average sum of average squares of the sum of the Stokes parameters, okay, is above certain value, the state is separable. And whenever this is equal to 0, this means that we have a perfect bright squeezed vacuum, formal bright squeezed vacuum, or perfect singlet, if you like. Okay, and so the idea is just to copy, and you will see that this idea, that's an important idea later. Okay, just to copy this. And so, obviously, if for a singlet, let's say the singlets have perfect correlation. In this case, that means that if we find n photons here, let's say, and the measurement is the same on the measurement setting is the same on the two sides, and whenever we measure n photons here and everything is ideal, we will measure n photons on the opposite exit of the polarizer there. Okay, so. Again, for a singlet, we can start, let's say, with EPR correlations, which are expressed like that. So that's how a singlet, perfect singlet, would also look like in terms of those squares, of those average squares of those new Stokes parameters. But the entanglement condition is different. It's a funny thing. You see, once you know this, it's very easy to guess how this one looks like, because everything is just, you don't average the total photon number, but 1 over total photon number. And now, let's say, okay, new condition. Click balance. Balance. Okay. Okay. New condition. Okay. And then it turns out that this condition, let's say we were first trying some artificial noises, blah, 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 like theoreticians, okay? But I think something that may be convincing to you, we simply applied the following noise, that we lose photons, okay? That we have finite detection efficiency. And this condition for this bright squeeze vacuum, formal bright squeeze vacuum state, can detect in the otherwise ideal situations entanglement only when the detection efficiency is higher than 1/10. And that's a very symbolic number. It's not something that is, it's a very important number. In that case, we can go on that. Okay? And as a matter of fact, if we go to just components, those n photon components, so basically if we have very high number, just one, you prepare a state somehow that only one component emerges. Okay? I don't know how you will do it, but perhaps in 100 years somebody will do it. Okay? Then our detection efficiency is crucial detection efficiency for entanglement is very low, while theirs is 1/10 for the same state. Okay, and so the next thing that we did, okay, we were happy, okay, and then we cooked up the following rule that we can. So we had just one and rewritten entanglement conditions with the new Stokes parameters, which was based on this Baumeister. And now we decided, let's go for infinitely many. Okay, and the rule is like that. Okay, you take, I'm talking about again polarization. You take any entanglement witness, which Horodecki's or whoever invented, and for 2 qubits, and then you have expanded in terms of the operator bases, which are the Pauli matrices, and then you replace them with our Stokes parameters. With our Stokes parameters, that means those normalized. And it works smoothly. And here's the most difficult, in a way, example, because my friend January Palm and his team, they have derived many years ago. It's not so well known. An inequality which is satisfied for any separable states, and this is absolutely equivalent to this partial transpose criterion. Okay, so this is the universal inequality that must be satisfied by any separable state of 2 qubits. And of course, then we rewrite it like that. Of course, not blindly. We have to prove that it's really like that, and the proof is not that difficult. You can find it. You will find it this month in physical review. And now, here we decided. The thing is that, let's say, in case of that condition, the stronger we drive, the weaker is the entanglement. This indicator is weaker. But we have created also the same type of and is derived, okay, entanglement conditions for all Stokes parameters. And now we can compare. So you see, with the old Stokes parameters, here is the pumping rate. Okay, let's say that's the entanglement. That's the separability threshold. Okay, that's the value the left-hand side in the inequality. So that's the separability threshold. With all parameters, the violation of separability is much less pronounced than in case of redefining. So as you see, they are better. Okay? And now we still work on it a little bit. You know that we went into the phase where some of the experiments that were dreamed about in the past, not only during the Einstein era, but even in the era when we met in Innsbruck. And we, for example, dreamt me a little bit more about multiport beam splitter. Okay, and even Michael Reck built one which was completely unstable and was following any current of air in its phase fluctuations. But now I think with the integrated optics you can do quite stable multiport interferometers. Okay, so just imagine that we can have a source that have 3 beams which are correlated, and it's again. Say you can do it with parametric down conversion, and for example, 3 output multiport beam splitters. Okay, and then we decided that we build several multiport beam splitters which are leading to unbiased basis. So we have to have we follow the same ideas like in the case of polarization. Okay, and then we, for example, build such an operator which is rated here times 1, rate, that's again number of photons at the given run detected at this detector divided over total number of photons detected in the given run in all 3 detectors. Okay, so that's why I call them rate operators. Then if the counts are here, it's omega. If the counts are here, it's omega squared. Okay, so and such ideas were, for example, let's say advocated for by Anton and Danny since early 90s, and in one of my 97 papers, let's say we were dreaming about things like that. And those things, here we can also observe Einstein-Podolsky correlations. And then, let's say that's a little bit different condition. Let's say we have derived such a nice condition. Again, it depends on the averages inverse of the total photon number. And of course, if we build a similar condition for standard Stokes parameters, it is weaker and so on. And now let me come. So then I will make a, let's say, a quick slideshow. Okay. So one thing that I can explain you during coffee time or over the beer. So why this number 1/3 is so funny? Okay. So just to fix your imagination, imagine that you have the last experiments. You remember in the experiment we had 3, let's say, dimensional interferometers. Okay, and just imagine that we have a kind of beam splitter that splits the signal evenly into 3 situations where we have 4 situations, and we have 4 complementary situations. Okay, so if we build something like that on the other side, let's say we could think that we have all on our optical table, okay, all measurements required. And it turns out that and of course, just look that the splitting acts like if here was a lower detection efficiency, okay, because some photons instead of coming here will come here. And it turns out that in our case, we can detect entanglement in an experiment which has, let's say, 4 such stations on that side and 4 such stations on this side without changing the inequality, whereas in the case of old Stokes parameters, such experiment would never ever detect entanglement. Okay. And the other thing it has been accepted this month is that we also try to apply this to Hongo-Mandel dip, so something that's totally unrelated to polarization, okay? And even unbiased basis, things like that. And it turns out that Hongo-Mandel dip is much more visible, okay? So we, instead of treating it as a correlation of intensities in the output A and B, we always divide each of those measurements by the total number. And then you see how clear that our Hongo-Mandel experiment visibility is much clearer than in the classical case. And the funny thing is, it's extremely resistant with respect to losses. Okay. So here are our graphs with the new approach, and that's the standard approach. Okay, so we beat them even. And what is very important, we can apply also that to other entanglement weaknesses, which are called Bell inequalities. And we can with this approach we can cure an old approach by Reed and Walls of 1986, where they derived Bell inequalities for optical fields, and those Bell inequalities were based on some additional assumptions, so they were really not Bell inequalities, but bona fide Bell inequalities. Whereas within our approach, which is based on those Stokes parameters in case of polarization experiments, we have two lovely things. One thing is we do not have this additional assumption. Details later. And the other thing is, surprisingly, usually additional assumptions allow you to violate your Bell inequality. But in our, so this is the kind of visibility, that's violation threshold of CHSH inequality. That's Reed-Walls assumption with, approach with additional assumptions. That's our with the modified Stokes parameters without any assumptions. So as you see, we gain twofold. Not only we beat, we can show violation of Bell inequalities for larger pumpings, but higher pumping, but also we do not have any additional assumptions, which were quite reasonable, but there's no reason for them to hold in local realistic discussion. And so as you see, so that's end of my, let's say, commercial about new approach to Stokes parameter.
Time for a question.
Can the advantage of your redefined Stokes parameters just be traced to the idea that by post-selecting out the vacuum, you're effectively creating?
No. Just sorry. So you see, perhaps I will have this. Okay. So as you see, it is the more pronounced, the less vacuum we have. So eliminating vacuum doesn't matter. Okay. So this is quite strong pumping already. Okay. So basically we have much less vacuum. The funny thing is when we have a lot of vacuum events. Okay, so we just have two particle, let's say one singlet emission, okay, one two particles emission. The two approaches are basically the same. Okay, so it works when you have let's say in the regions where you have undefined photon numbers. Okay, those Stokes parameters start to diverge because of their definition from the original ones when your total number of photons is undefined. So your state is a superposition of many components or mixture, doesn't matter. Of many components with different total number of photons. Okay? So it's not different.
Just a quick one. Is there any connection to measurement of parity?
Let's say, so you mean this approach with so-called pseudo-spin approach? Let's say, So this approach is, let's say, I would dare to say, much better than the pseudo-spin, because pseudo-spin is simply -1 to the number of photons. Okay? And just look that if you lose one photon, okay, then your value flips totally. You have completely opposite result. And the lovely thing, and that's one of the reasons why you have better things, if we lose one photon, then our value changes a little bit. And the funny thing is, just look that sometimes it doesn't change at all. Because look at the following, that we are to, let's say, in theory, we should have had, let's say, 7 photons, 3 here, 4 there, okay? And then we calculate our parameters, which are, let's say, 4/7 minus 3/7 for the group. Okay, and then we lose one of the photons. Okay, then the funny thing is that we shall get, for example, 3 here and 3 here. Okay, but it's still divided over 6. So the damage is very small. And the loveliest thing is that in case of perfect correlations, the damage is almost non-existent.
Okay. So we should thank Marek again and move to coffee. We were scheduled to have a 15-minute coffee break, or 20-minute coffee break. Maybe we'll make it 15. I'll clap my hands once we get to that. But thanking both the speakers this morning and